I'd like to invite the speakers, and we'll include Shelly to join. And we're going to have hopefully a general conversation about these, now that we've heard about these generalized environments. I want to first pose a question to the panel to get the conversation going. So given your experience in your different settings, how convinced are you that the microbiological observations that you're seeing are applicable to other types of buildings within that type and across types? So in the sense of sort of is every sample an island, or are there general intervention strategies that you can imagine being applicable to more than just what you've happened to sample?
I can take that partially. So in infant studies, for example, Guanam Dantas at WashU, he did a big study. It came out in Nature Micro a couple years back. But a lot of the organisms they see in infants are escape organisms. And then a lot of organisms you see in a lot of hospital-acquired infections are escape organisms. So I think that the environmental pressures of stringent cleaning with compounds and different detergents, like select for a certain type of island, if you will. And then differences you see across different parts of the hospital might be these dispersal events that could introduce. But I think that there's a strong selective pressure for intensive care wards particularly, but how that translates to other building environments, I think it's a very, very unique system that is not like many other built environments. Yeah.
Yeah, I think that the different environments are going to have different microbial communities. I don't think there's a lot of crossover. I was interested in Jessica's paper that showed, was it nursing homes had much lower indoor diversity than outdoor diversity, which is opposite of homes. And then you imagine jails and homeless shelters and buses, and I don't think there's going to be a lot of crossover.
I think the question was about intervention strategies. So yes, so I would say one of the main intervention for mold is, I think it would be equal to any building, is keep the moisture out. Because if you have moisture, then there's always kind of enough nutrients. So moisture, controlling the moisture is the one intervention strategy that can go across to many different types of environments.
Yeah, compared to all other earth things, we are still in infant stage because we have only few samples from there, to know the total microbes using molecular methods. But we do have 20 years worth of environmental survey from space station using culture-based analysis. So that has been appropriately documented, and then they have shown what we have seen in the molecular methods, and we are seeing more than that too. To compare a space station with any of the things here, I would say hospital microbiome may be the closest. Number one is hospital microbiome. Even though the patient wants to open the ventilation, sometimes it may not be able to do that because of obvious reason, because they are immunocompromised. So in that case, space station, astronauts are all very healthy individuals before fly, but they are immunocompromised under the microgravity because they do not know where the flow is going from the top, head to toe because of the gravity issue. So we also shown virus reinactivation in the space. In other words, before they fly, VZV and EBV are normal level, but 3 days before fly, they got anxious and they are stressed because they are not medically insured. Life insurance is not there for them anyway. They write off their life. Anyway, so because of that anxiety, the inactivation of this and reactivation of this virus coming. But when they are In the space station, if somebody is there for 6 months, it is not high. But 3 days before they descend, again it starts. So the stress is a big thing for them in terms of their own microbiome.
Okay, so it sounds like in terms of specific taxonomic composition, you think each sort of generalizable building type will be different, but there might be some general processes that might be applicable across types. The one mentioned, water will lead to growth.
And can I add ventilation? I think that's huge. To increase ventilation, it will really be a process that you can use across all environments to improve the indoor environment.
To improve in terms of?
The health and air quality.
Okay, I mean, I can imagine ventilation bringing more of what's outdoors in, but what outdoors is going to be very variable, right?
Well, if
Well-
people are allergic to the outdoor mold,
Yeah.
you don't want to bring them in. So
Yeah.
in that case, you want to filter and keep the windows and doors closed. So depends.
Okay,
on
so
the health
maybe this is a
outcome.
good point to,
Yeah, I think ventilation is a good thing to discuss. It's a huge topic. You know, if you're living in a city with high ozone, you need to filter the ozone. But in general, we've seen that increased ventilation rates improves the health of the people in the building, decreasing sick building syndrome, affecting allergies and asthma. So there's a lot of work that shows that. And Mark Mandel just left.
I have a glossary question for Bubba. Chuck Haas and I were talking at the break and discussing the need for a glossary, and one of the terms that came up when you were presenting your data, Bubba, was the term biomass, and you were relating that to amplicons. So can you define biomass given amplicons on your basis for it? What do you mean when you say that term?
Yeah, so with my work, it was just, I think in the field, qPCR has been more frequent, just taking primers and seeing how they amplify in a qPCR machine, and we can go into that further. I was using digital PCR, which is very similar to qPCR, but it's basically taking a conserved region and counting how many copies you have at the end of does that answer your question, or?
No, I know I do know what PCR does, but I guess what I was trying to get to is where does the mass figure into what you're responding to, what you're presenting, other
Okay.
than amplicons?
Right,
Where's the
so-
mass part of that?
So for example, are you suggesting we should have this type of physical weights of mass? Is that what you're suggesting, or?
I'm asking you to define mass in the context of presenting amplicons. That's all I
So
am.
the biomass, for example, I'll take sinks for example. We see more biomass on some days than other days. So that would suggest that across days there may be growth of the microbial population based on quantifying a conserved gene within their genome. So it's just an accumulation of these genes in a concentrated area inferring growth.
Okay, but no mass correlation,
No mass correlation.
nothing to do with protein, fat, carbohydrate, nothing. It's just straight
Not with that
amplicon
estimate.
cons.
It's just straight, there's a gene on this chromosomal backbone, how many times can we count
Okay.
it in one place?
I just saw biomass on several slides, and it's just straight
It's a good point, yeah.
amplicon count.
Straight
Okay,
template counting,
Got it.
basically. Yeah.
I have a question for Tiina. It's about these submicron fungal particles. This drives some people crazy because it shows that they're there. There seems like there's a lot of them, but we don't really have any way to detect them, or do we? And the other kind of follow-up is, are there any ideas if these particles are immunogenic?
Yeah, good point. There are ways to detect them, but not any good way to really account all of them. We have used beta-glucan and endotoxin assay, and have seen about the same biomass in the below 1 micrometer size range than above 1 micrometer size range. There was a group in Texas who showed mycotoxins There, and then we did some preliminary experiments with antibodies, fungal specific antibodies, but there the issue is the detection limit. So definitely there is a need to have some method to analyze. I don't think the sequencing would be able to. So you need to look at the components of the and it's mostly from the cell wall. Seems to be that it's mostly from the cell walls of fungi. And they are all of these that I mentioned: endotoxin, beta-glucan, antibodies, antigens, and then mycotoxins. They can affect health. And we know, of course, from the particle data, aerosol data, outdoor aerosol data, that the smaller particles can be actually more harmful than the larger particles. So it's definitely something to look into a little bit more.
So in this case, Tiina, you mean true mass. This is mass of protein that's...
Endotoxin beta-glucan is mass.
Right, right.
Number-wise, the numbers can be, we've seen 1,000 times higher numbers in the fragment size range than in the spore size range. So number-wise, the concentration is way higher. But mass it could be about the same as in worst cases as the spore size range.
So this is a question about beneficial interventions for the indoor microbiome. So I think it's clear that increasing outdoor air ventilation is beneficial for occupants of a building because it reduces symptoms, it reduces infectious disease, and things like that. But do any of you, this would be a question for anyone, do any of you know any reason why increasing outdoor air ventilation would be beneficial because of things that are brought in from the outside?
I don't have any hard data, but if you had a lot of beta-glucan outdoors and you bring it indoors, could be potentially protected, but I don't have any data to support that.
Space station cannot be opened.
So actually that last comment brings me to my question about your observation on the space station that you get a seemingly lower proportion of fungi than bacteria. And I'm wondering if that could be a possible explanation, is that since I would imagine that most of the microbes on the space station come from human beings and are shed by human. I wonder if that could be reflective of that. I don't know how much fungi a human body will shed, but I imagine that it would probably be a much higher proportion of bacteria. So I'm wondering if that's a possible explanation, since nothing really can come in or out.
That may be one, but at the same time, humans are not the only source of microbial transfer into the space station. We are bringing cargo. We are taking veggies, to grow, plant materials to grow up there. So those are the possible sources of the things. But it will start, once it get accumulated, then it will be a problem.
But wouldn't you say...
Right now, it is not.
But wouldn't you say humans are the only source of constantly renewing microbial populations?
Yeah, correct, that is true. So humans are the one constantly exchanged, for various reasons. That is absolutely right. But tomorrow, if you are going to have this station, right now is 20 plus years. Right now, if you have another 20 years, maybe mold would outgrow the, bacteria. I'm not sure yet. That's positively happened for Mir, right?
So in the NICU environments and some of these extreme environments, you see this continuous pattern of, you're saying these escape organisms. They seem to do extremely well in highly desiccated environments that have been cleaned a lot. They're clearly, I guess, making some kind of biofilm. They last for a huge amount of time on surfaces. Some of them come from the skin. I noticed that over time, some of the studies we've done show that if you just let things go, you remove all the humans, all you're left with are the sort of skin bacteria that seem to just make it forever. And it seems like you've sort of answered this whole idea of inanimate hospital environments there was a question of whether you could things really lived on surfaces for a long time. It sounds like you've settled that. They really last for a long time, and you can theoretically transfer them. So, what I'm wondering is that, if you do have those things that are stuck in these surfaces where there's really not much to eat, actually, and do you think opening the windows and stuff is actually going to, is there any way you could test whether that would actually somehow outcompete and take over those biofilms? Because that would be a really, so you know they're there, you know who's there, you know why they're there. You could actually ask whether that would disappear as you started adding things that come from soil organisms, which are also really tough. Have you thought of doing anything like that to see, if this idea is correct, it should somehow outcompete those, right, and make it better?
Yeah, I think what I presented on Jack Gilbert's before, during, and after a hospital opening, I think maybe a better strategy would be to try to get there before those biofilms form, because they are really hard to remove. In terms of having new organisms being introduced and almost predating or like eating the biofilm, metabolizing them, and then displacing them, I think it would be an interesting experiment. It would be very difficult to implement in the hospital setting, but maybe starting with mice models where you could try to emulate something similar might be a good place to start. But yeah, I think prevention before it gets to that phase may be even a better intervention strategy. Yeah.
One idea that I might throw out there are other regions in the world that they use natural ventilation in hospitals, and it might be worth looking at the microbiology in those hospitals compared to the U.S. hospitals where we don't use natural ventilation. And I also might add that ultraviolet germicidal irradiation is an interesting intervention in very specialized environments, such as NICUs. There's a nice paper that shows reduced colonization of lots of surfaces in the NICU and reduced pneumonia in the babies that had the UV compared to those that didn't. And if I could also say, I'm thinking about Mark Mandel's comment, and I wanted to throw out the idea that, especially from Jordan's paper, that increased diversity seems to be good in some cases to be protective for health, and so that in naturally ventilated buildings you do see an increase in diversity, and so there may be something interesting there to explore.
Absolutely. Clean is not merrier for sure. So I showed you only space station, but we are also doing the spacecraft assembly clean room maintenance for Mars and other spacecraft development. So we keep it extremely clean. So basically what we are doing is we are developing a robust bug that is actually problematic tomorrow for us. So some of the spore formers that we are seeing, we isolated a highly UV resistant microbe. It is at strain level though. It is definitely the cleaning that we are using it is making it more resistant to UV. And this one is the champion right now, is from the California here, in terms of UV resistance, and anything that you have right now, Bacillus pumilus FR32, we have done so much of work on it. And as I said, cleaner is not always the merrier, but you cannot build your spacecraft on your garage, so you have to be careful there.
I'd like to throw out for discussion the use of the word biofilm. I think it's being used in a very different sense in some of the discussions today than I'm used to hearing. Biofilms exist in natural streams on rock surfaces and in pipes and in dental tubes and environments like that. The environments you're talking about are, even if they're humid, they're relatively dry compared to those. And so I wonder if it's better off to avoid the term biofilm unless you can actually prove that there's a demonstrable structure that's similar to what we observe in those other venues, when rather what you have is persistent and refractory fomites.
I don't know whether you have seen some of the space station surfaces that the astronaut actually, they cannot take shower, as you know. So they have to use the wet towel and then, clean their body and other things.
Certainly in that environment, right?
So they take it and put it in a refrigerator side, and the astronaut didn't take that towel for 3 days. The 4th day they are seeing the whole biofilm growth on it. And also I understand, so it is loosely used, and what you are talking is microbial mat. So that is more in environmental surface. But the start of the biofilm, you need something to adhere into some hard surface. From there, it will develop later.
But,
So early prevention.
let me keep the ISS aside, but for the other venues, I really question whether or not you're getting the biofilm formation, on door handles and so on and so forth. And rather, you're getting, instead of fomite that's maybe embedding itself into protrusions or surface roughness or some other surface microstructure.
So I guess my question could you further define fomite of the structure? So if you look at the paper that I referenced, the scanning electron micrographs that they show, it's a very complex, thick mat of complicated extracellular polysaccharide matrices, and there's lots of different types of cellular morphologies embedded in this mat of polysaccharides. And to me, it looks like a biofilm, and the stains that they're using suggest that they're a living biofilm, at least a film of a matrix of some sort of likely polysaccharides embedded with different morphologies of cells. So I guess I'm not familiar with
Okay. So, in that case, yeah, I buy that, it's demonstrable evidence of a biofilm. A fomite is simply an inanimate surface that may have transmissible organisms that people can become exposed to. And you get persistence on a fomite typically when the surface is rough.
So I think, if I can interrupt, we should let Rachel pose maybe one more question to the panel and then move to the breakout sessions, because we're already a little bit overdue.
Okay. Yeah, so another question I had was, given your building type, what are some of sort of the main questions to be answered, and did those questions come to mind when you were hearing about another building type that were common? Or if it's unique to your environment, what are some of those big questions that remain to you?
I'll just go. So again, back on the escape organisms, just because you have escape organisms in your environment doesn't mean you're going to get really sick. And a lot of the babies that we assay don't end up getting really sick. So I think doing better characterization of the strains in this population, and also the strains and keep in mind, all the data that I showed was just in the infant gut. We have data coming out hopefully soon in the room environment, looking at whole genomes and their strain structure. But further understanding why that matters is important, I think.
So another question of exposure? Asking, why are they getting some exposed to some microbes and not others?
Well,
Or
up
is
into
the
this point,
implication-
up into this point, a lot of the times we don't know down to the strain level. And using certain assays you can, but we don't know if the strain is exactly coming from the room in a lot of our data yet. And so it would be exposure. Is it coming directly from where? Is a big question that still needs to be determined.
What about you in home?
I don't know if this is specific to homes. It could be common to other environments, but I think this protective versus detrimental effect is definitely something that still needs further study. So when the same type of exposure is protective, could be the age of the population, the genetics, concentration, size, and we don't really know much about that. So I think that's one open question. And of course the fragments that was already brought up.
And if I could add, the co-exposures and the exacerbation of exposures was very interesting. I imagine if you're exposed to high levels of ozone, and then you're also exposed to some toxin from a biological source, there could be an exacerbation there that we need to look at, which we don't know anything about, the chemical versus microbiological exposure.
So Tiina, I just wanted to ask, and Jordan and I were just talking about this, is what protective effects that are suggested so far, is it pretty much limited to early life?
In our study, we showed the beta-glucan,
Yeah.
high concentration of beta-glucan, Jordan Petchias. I don't know if it can be said protective, but the diversity.
Sorry.
And
Yeah.
then I did not talk about the endotoxin. There are studies in Europe in agricultural environments where they contributed endotoxin exposure to be protective against pathogen.
But everything, is most of the evidence associated with very early life? That was my question. It seems that both with animals and what few studies we have, biochemicals or whole cell diversity, it seems to be early life only, at least right now. Is that a fair statement?
Mostly. I think I remember seeing one paper also in adults that endotoxin had an inverse association, but you're right. So it is mostly the early exposure. That is, but how early? That's a question.
About damp building studies and office buildings, as you get to the higher endotoxin levels, we've seen turns negative association with symptoms, respiratory symptoms. So that's in adults, because we study adults. Yeah.
Okay, so we're going to move to breakout sessions now. Everybody has a little sticker on their name badge. If you can please go with the group that you were assigned to, there was some method to that madness. You're going to go outside of this room, take a left and go all the way down the hallway, and each room will have a sticker associated with it. And we're going to come back here at like 5:15.